Uh, Good evening, everyone. Myself, Rahul Daya, and I am delighted to welcome you all to day 5 of the AICT ATAL Faculty Development Program on Next Generation Communication for 6G and beyond. We have successfully completed 4 days of highly enriching and impactful sessions. Today, we proceed with the 3 more exciting and application-oriented sessions. We extend a warm welcome to all faculty members, research scholars, and participants joining us online from various institutions. Your active participation is truly appreciated. To begin today's session, it is my honor to introduce our first speaker, Professor Himanshu Bhushan Mishra from IIT ISM Dhanbad. He is an associate professor in the Department of Electronics Engineering at the IIT ISM Dhanbad. He completed his PhD in Electrical Engineering from IIT Kanpur, specializing in signal processing and wireless communication. He also holds an MTech from NIT Rourkela. Professor Mishra's research focuses on advanced wireless communication, including 4G, 5G, and beyond 5G system, OTFS, FBMC, MIMO, and massive MIMO, and machine learning for communication systems. He has led several sponsored research projects funded by DST, SERV, FRS, and other national agencies. Professor Mishra has previous experience working with IIT Kanpur, Qualcomm India, and has delivered invited talks at NIT Rourkela, NIT Trichy, IIC Bangalore, and DOT organized FDPs. Professor Mishra will be speaking on the topic MIMO Communication. Sir, we are delighted to have you. I request Professor Himanshu Bhushan Mishra to begin the session. Sir, the stage is yours, sir.
Thank you. So my screen is visible? Is my screen visible?
Yes, sir.
Yeah, it is visible.
Okay, thank you. Okay, good evening to all. Here I would like to deliver this lecture on how we can physical layer technologies will be evolving from 3G to 6G wireless system. So let us go a little bit background on what will be there in the history of wireless communication standard. So as you can see, first 1G based on there is 3 technologies. One is AMPS, TSES. These are mostly based on the analog communication. So whenever we are moving to 2G, then digital communication started. So there are key technologies known as your GSM, DAMS, PDC, CDMA. Then once 3G, then we have started there is a communication known as uplink and downlink. How we can communicate like there is a duplexing technique started that is known as FDD and TDD. This is like duplexing techniques. That will means one time in FDD, 2 different frequencies will be allotted for uplink and downlink. That is one frequency will be for uplink at a time, another frequency will be downlink. Both will be communicating at same time. Then in case of TDD, what will happen that an uplink communication happen, one time slot will be allotted, and for downlink another time slot will be allotted. So they will communicate at same frequency. Okay, these are the key differences of FDD and TDD, and there are also positive and negative points for both these techniques. Then we have also CDMA 2000. So many of you know all these things. So let us come next 4G. So there is a huge difference from 3G to 4G, that is data rate enhancing, lot of data rate we are getting, lot of reliability we got. But that is due to one main important physical layer technology that came, that is known as OFDM, orthogonal frequency division multiplexing. And also we have it was introduced at that time, that is known as MIMO technology, or you can tell multiple input multiple output antennas. That means both the transmitter and receiver has more than one antennas. Okay, so that is also known as antenna diversity. Antenna diversity means you can have one antenna at one side and another side more antennas, or both side more than one antenna. So that is known as antenna diversity. Mostly this technology are key technologies for 4G. And after that, yeah, these are some spectrums for whatever they are in 1G. 2G is around 800 to 900 megahertz. Then when we are going to 3G, it is focused to 2 gigahertz band. So when you 3G to 4G we are going, then some few additional both lower and higher frequencies, few additional bands are added. Like it has spanned from 450 megahertz to around 6 gigahertz. Okay, so these are like, and all of us know that at lower frequency there is a difference between lower frequency band and higher frequency band. Bands at lower frequency are good, have good propagation properties. However, at higher frequency will go, they'll be difficult to propagate. That means many absorbs, easily absorbed by a lot of obstacles. Okay, so and this is what is 5G. Next, 5G is there is a key three use cases of 5G. One is known as enhanced mobile broadband, and another one is URLLC or ultra reliable low latency. Another one is massive machine type communication. These three use cases will have different applications. Like EMBB, if you are focusing for high data rate and high traffic volume, then you can go for this EMBB. So that's the key difference from 4G to 5G. 5G, 4G, like they 5G, whatever they have for each use case, they have different technology has been developed. Actually, that is a one important point of 5G, that we can, it is became more flexible than 4G, and lot of bandwidth, like one particular bandwidth has been allotted in 4G, but now we have bandwidth parts, like you can have different bandwidth as per the requirement of the user you can give. That is the very interesting thing of 5G. So like you can see, for high data rate you can go for EMBB. If you are connecting massive number of devices, you can go for MMTC. But another thing, ultra reliable low latency, that is also key technology of 5G, where you can have that means you want to a low latency communication. For example, vehicle to vehicle communication. So that is some signal you are transmitting from one vehicle to another vehicle. So that should be very that should take very less time. Otherwise, there will be some accident may happen. Okay, before getting the signal from another vehicle to this vehicle. So that should be, first point is low latency. Second point is reliability. Reliability means how correctly you can detect the signal. So that two are the key point whenever we are dealing with URLLC technologies. Okay, so these are okay. Let us see some spectrums of 5G. 5G based on two different frequency ranges. One is your FR1 and FR2. FR1, what you have, it is 450 megahertz to 6 gigahertz, and it supports both FDD and TDD. I told that frequency division duplexing, FDD, and TDD is time division duplexing. There is also another band for 5G that is going to use, that is also known as millimeter wave band. That is from 24.25 to 52.6 gigahertz. In this range, you cannot go for FDD. Why? Because there is due to absorption, that high frequency, as I told you, that will get easily absorbed by a lot of obstacles. That's why this a thing is TDD. That is one reason for going TDD for case of millimeter wave. Then the maximum bandwidth of control channel, it is 400 megahertz for 5G. And number of subcarriers, when you're going for OFDM, I will discuss what is OFDM. So in OFDM, you can have number of subcarriers will be 3300. This number of subcarriers you can use maximum for 5G. And the FFT size, when you are going for OFDM, you have to be deal with FFT and IFFT. The size will be maximum 4096. And number of control channels, there is maximum 16. So you can play around it. That means there is a lot of flexibility over there. Maximum means you will not always use this much. That is, you can also less number this. Okay, so that is the concept of 5G bandwidth parts, so that we are not discussing over here. So another thing is what waveform technique has been used in 5G. We'll discuss here. One is that is known as CP-OFD. CP means cyclic prefix. Cyclic prefix, we'll discuss what is this. Okay, so CP OFDM for downlink. DL means the downlink communication. When you are communicating for base station to mobile phone, we'll go for the CP OFDM. Whereas when you're going for uplink, we'll use CPU OFDM along. Also, there is another technique that is known as DFT spreaded OFDM. Actually, this white came because generally, if you see OFDM, it has a high peak to average power ratio. This is a PAPR, or if you people know these things, PAPR is something like you have, it will require high power amplifier to make everything means otherwise signal will be get distorted. So PAPR will be very high for CPU OFDM. So therefore there is some DFT spreaded OFDM. That is some precoder will be used to OFDM side. That's why, because we are uplink transmitter is our mobile phone, right? So if you're high PAPR, so more power we require at the mobile phone. So it is very difficult in practice. So that's why people also using this DFT spreaded OFDM. But the key technology is OFDM only. And the multiple access that is they're using is OFDMA, orthogonal frequency division multiple access. That means for different frequency, you'll allocate different users. Okay, when you're communicating the multiple users, then this technology is used in 5G. So let us come to the key physical layer technology for 5G and 6G. We'll discuss all these technologies here. So one is MIMO, another one is massive MIMO technique, another one is OFDM, another one is millimeter wave. This red one we'll discuss here in this lecture, and we'll not discuss like integrated sensing and communication. Okay, let us millimeter wave will not discuss here. That is higher end communication. Whenever going millimeter wave means you have to be use antenna array along this to get a high beamforming gain. Then when you are going 6G, in 6G technologies, one is key modulation that is known as orthogonal time frequency space. Why this came? Because to get a reliable transmission for highly time varying channel. High time varying channel means whenever you are moving with high speed train, or you can tell the aircraft moving at a 900 meter per second, that kind of speed. So if you are going to communicate with that, it is very difficult in OFDM because there is a negative point that Doppler, once you arise the Doppler, so that will give a inter-carrier interference for OFDM. Therefore, you will not get that much of reliability if you use OFDM. Therefore, OTFS came into the picture. And another one is integrated sensing and communication. That is interesting technology for 6G, where you can both sensing and communication, both you can do by using a dual base station antenna. Another one is known as reflective intelligent surface. So that is you can tell as passive or active. There are a lot of variations of RIS. That is actually reflecting surface. By using this RIS concept, this is actually add-on technology. Okay, what will happen that whatever technology you are using, OFDM or whatever existing technology wireless you are using, you just put an RIS into that. What the RIS will give? RIS will give additional beamforming gain, and it has a key benefit that it can what program the wireless channel. That means you can modify according to your objective. If you want to achieve high data rate, high low probability of error, based on that you put your own objective, and accordingly you can you can get what modify the phase shift of the reflection coefficient of the RIS, and accordingly you will get a better reliable wireless system having high, or you can tell spectrally efficient wireless system. That means this is actually add-on technology that you add with any existing wireless to improve this performance. That means you'll get additional beamforming gain. So that is being taken, it is being mostly coming in 6G system. Okay, so let us come to so basics. So I would like to start some background basics of discrete wireless system so that you can be clear how it will getting evolved from a 3G system is to slowly into 4G, and how we are getting why this wireless system, as in what is the negative point of wireless system, and that how we are mitigating. Okay, let us first start. So there is, whenever we are designing a wireless system, there is a 2 points you have to be focused. There is a two important points. There is also another points. More points are also there, but two key parameters, or you can tell that, yeah, the key parameters. One is your throughput. Throughput is what? Bandwidth multiplied with spectral efficiency. The spectral efficiency means what? The unit is bits per second per hertz. So if you can design a wireless system which has a high spectral efficiency, automatically if you multiply the bandwidth, it will go for different bandwidth, so automatically we'll get a better throughput. So what we are doing, we are focusing highly spectral efficient wireless system. How to design this one? Another one is enhancing the reliability. Reliability means you can tell the bit error rate or a probability of error of receiving the signal should be very less. There should be less error. Then you can tell that your reliability is another. Also a lot of other parameters like energy efficiency and other things are also there, but these two are very important. Whenever you are designing some wireless system, people will ask what data rate it is providing. Okay, what is the reliability it is providing? So that's why we have a throughput and reliability. That is two critical parameters. Okay, so next is in wireless system, there is basically You can see the wireless, due to the movement propagation of electromagnetic signal, what will happen? So there is a two different parameters will come into the picture. One is due to multipath nature of the channel. What is the multipath? Because signals will get scattered, right? It will get refracted by different objects. It will getting added at the receiver. So that's why you will get that is the known as the reason due to the multipath nature of the channel. That is the multipath. So two nature of the channels we have. One is multipath nature. Another one is time varying nature. Okay, time varying one, it will come when you are moving. Okay, when you are moving, then both multipath and time varying will come. When you are sitting inside the room, only multipath will be there. That means these two are the important nature of the channel where which will create a problem, which is creating problem for establishing the wireless system. So whenever you are dealing with, whenever due to multipath nature, your channel can be of flat fading or frequency selective fading. Okay, flat fading will happen. There is some reason. So there is some one important parameters. One is known as delay spread. Delay spread, its inverse is the coherence bandwidth. So these are the key parameters based on the how much is the symbol duration, and if it is greater than the delay spread, you will get flat fading. That means you can tell a single tap fading. Then frequency selective. Frequency selective means you have a multiple path, multi taps. If symbol duration lesser than the delay spread, then you'll get the frequency selective fading. Then due to the time varying nature, you can have channel can be either slow fading or it is fast fading. Fast fading you can tell is a highly varying time. Means you are moving with high speed, so you'll get high Doppler. That is gives rise to fast fading. Why it will, how it will come? It is the you can put the condition like coherence time. Coherence time is the time during which channel is approximately constant. So if it is adding less than symbol duration, so that you have the fast fading. If it is greater than symbol duration, it is a slow fading. This coherence time less or greater, smaller or larger, that depends on your velocity, right? So how much the mobile phone, the relative velocity between the transmitter and receiver is high or low. If it is very high, there is a lot of formula you can see, like Doppler shape related with the carrier frequency, velocity. So you will get accordingly slow fading and fast fading. Now the question is, based on this, so how many fadings you got here? Two from multipart, two from the time varying. So you can have four different fadings, combine one from each. That means your channel can be either flat and slow. That means you can have four different. See, one you take frequency selective and fast. One you took from where? Here, frequency selective. Then another one is fast. You club it, you have frequency selective or fast, or frequency selective and slow. Another one is frequency flat and fast, and flat and slow. So these four different systems, whenever we are designing a wireless system, we have to be write a basic system model of input and output. That means input signal, there is a channel, then there is output. So what is the relationship, mathematical relationship between input signal and output signal, including the channel? If we consider a four different channel scenario, that means in practice, if you are sitting inside a room where actually frequency selective and slow fading channel we have. If you are going outside the room, moving with high speed, you can have frequency selective and fast fading. So these two are actually most practical channels. This second and fast. Generally, we very less you will get frequency flat fading, flat and fast. Flat you will generally get if you have a highly directional antenna. That means there is a line of sight path. Then you can tell you have one tap channel. If you had a lot of multipaths are there, so you will not get a one tap flat fading channel. You will get a frequency selective. So one and two, these two are mostly more practical system. Second one, you will sitting inside the room, you are moving at a very slow, like pedestrian movement you are doing, walking. So that means you are at this scenario, frequency selective and slow fading. Now, what is the mathematical relationship for this? If you have x you take as the transmitted signal, z you take as the channel variable, y you take as the received signal. So if you are the second equation, you see equation this one, so you will get clear. So your channel is actually a LTA system. If you are dealing with slow fading channel, that channel is a linear time varying system. Time invariant, LTI, linear time invariant. That means if the input is X, okay, there's a, if you have a frequency selective, you will get multiple taps. Multi taps means your channel filter up more than, it is a finite impulse response filter, but it is more than one tap. That means you can 3, 4 you can take. That means what will happen if LTI system input is there, so it will be a linear convolution. So that's the equation. So the channel in input signal, linear convolution added with the noise, that is the receive signal. Here what happens, that is not actually linear convolution for fast padding. Why the channel, you can see the GL, this means the channel at lth tap, or you can tell lth delay in a layman form. More means lth tap is a better thing to tell, or you can tell lth delay point the channel. Here you can tell lth delay at one time instant n. Since it is time varying, you will get a different time at different time at same tab. Lth tab will vary because that is a time varying system. That's why this is a LTV system channel once you're going to the fast padding scenario. But if we know that if the channel is the system, DSP means that system is a LTV, then input or output, that is not linear convolution, right? So this is actually not linear convolution. If it's LTI, that is a linear convolution relationship. Okay, so that's why this relationship will matter when you are designing a wireless system. Okay, so let us come to the next one. If flat and fast were very simple. Flat fading means you are just multiply one component of channel with transmitted signal. So Gn, fast, it is function of time. Okay, flat and slow, that means it is not a function of time. You can tell it is constant. That means constant over a long duration. That's why where you can remove the function of time. Why? Because it is constant. See, so that's why you can simply a variable multiplied with the transmitted signal. Okay, then each of these variable, this variable is a random variable, GL. We are generally consider this as a Gaussian variable due to multipath getting added at some lth delay. Lot of multipaths having same delay that is getting added. So what you will get? You will get a, by applying central limit theorem, you will get this is a Gaussian random variable, all these channel tabs. Okay, so then let us come to, for this case, let us first focus only this one, second one. Let us focus frequency selective and slow fading. You will focus that what you have at any time instant, receive time, mth time, what you have, your channel, right? Channel at 0 into x of m, plus there is some interference from the other symbols plus noise. That means at mth time instant, your desired signal is this one, transmitted signal at mth time instant, this one. However, you are getting some additional interferences from the other signal. That is happening because of the frequency selective nature of the channel, or you have multi tabs, or you can tell that your delay spread is higher than the symbol duration, so that present symbol will get interfered by the previous symbols. That is happening. This is known as inter-symbol interference. So then once this will be there, you cannot decode a transmitted signal very reliably. So that's why what will happen, there is a technology known as OFDM came into the picture. So OFDM reduces, completely mitigates the inter-symbol interference. Okay. So we'll discuss OFDM later. So before that, let us discuss a very fundamental thing, what is known as effect of fading channel on the reliability. So let us come to the point. What is a AWGN system? If you don't have a wireless channel, what is your transmitted signal is X, that is only get, means there is something into X, but that is not random in nature. That you, or you can tell X plus some noise. Okay, where the noise we are considering as additive white Gaussian noise is Gaussian noise. This is a very simple channel where you don't have wireless channel system. This is a AWGN system. That means X plus noise. You will have this, you will analyze, let us take that transmitted signal has power EX, and noise has 0, mean and variance and not. So what will happen? The SNR, signal power, signal energy by, or you can take signal power by the noise power, you can take as EX by N naught. So what is the bit error rate formula? If you can derive the probability of error, if you know that is function, that is known as Q function of square root of SNR. What you observe that Q function is a decreasing function. If you increase SNR, Q function will be decreasing. So you will get BR some kind of like this. If you increasing SNR like this, you will get bit error rate like this. Okay. Let us come to, this is for case of AWGN. You don't have any fading channel. Let us come to the fading, simple fading. I told you what this is a flat fading system. Okay, for analyzing the bit error rate, the difference from the AWGN to the fading, we have considered a very simple scenario. Y is equal to HX. H is the fading into channel. plus H into X, the transmit symbol, plus noise. So H is a complex Gaussian variable. So okay, let us see what is SI and SNR, signal to noise ratio. Considering the channel, it is H mod square into EX you can take. So I have considered here PU, whatever you can take, you can EX divided by N naught. This is the SNR, instantaneous SNR. Why? Because it is considering instantaneous value of the channel, which is random in nature. It will vary. So if you consider that, what will happen? What is the probability of error? Is probability of error, instantaneous probability of error will be Q function of SINR instantaneous. Okay. But however, we know we have to find the average probability of error. That average probability of error, if you derive using this instantaneous probability of error, we will get 1 by 2 SNR. That means you just focus these two things. 1 by 2 SNR or approximately 1 by SNR is the BER or bit error rate for Rayleigh fading channel, whereas Q function of square root of SNR is the bit error rate for AWGN channel. These two are the difference you see. This is significant difference. This is a highly decreasing function, whereas this is a linearly decreasing function. So you can see here like this kind of approximately. So you will get, so this is, see, at 5 dB, or you can tell at 5 dB, you are getting approximately around 10 to the power minus 2 bit error rate. How much you are getting for fading channel? This is the fading channel, 1 by 2 SNR. This is the approximately the 1 by 2 SNR plot is this. So you see at 5 dB, how much you are getting for there? 10 to the power minus 1. Here 10 to the power minus 2. To get 10 to the power minus 2, how much extra dB you will require for case of fading? You can go here. Till 20 dB also you are not getting. You are here at 10, 20 dB. Till 20 dB, you are at 20 dB. Still you are not getting 10 to the power minus 2 bit rate. See how much penalty you have to pay to get at least 10 to the power minus 2 bit rate. 10 to the minus 2 means what? 1 by. So that means this gives us that how much we are, how much penalty means how much extra power we have to give to achieve a bit rate which will be close to the AWGN. Okay, that is the key point of fading channel. So fading channel, why it is happening? So why this bit error rate is too much of degrading than the AWGN? Why it is happening? The main reason is the probability of deep fade. There is a deep fade. What is the meaning of deep fade concept? So it is deep fade means what? If you are transmitting this, look here, this H is random in nature. So due to this H, what will happen? There is a instantaneous signal power. What is signal power? H mod square into power of X, right? There is a noise power, sigma square or n naught, whatever you are taking. This, if the signal power is greater than the noise power, then it is fine. Then you can easily decode the transmit signal. If the signal power is less than the noise power, you cannot decode the transmit signal. So that is the key point. If H mod square into EX, this is the transmitted signal power. This is the noise power. If this is greater than, then your probability of error is very less, or you can decode easily, or your decoding probability will be more than the if you have a scenario which H mod square is less than the noise. Here what will happen? Your decode probability will be very less. That means you will get high probability of error. That is obvious. If actual signal is, the power of actual signal is less than the noise power, you cannot decode decoding probability will be, that means your getting error is very high. Why? Because noise is dominant there than the signal. So this is known as a deep fade scenario. Okay, this deep fade scenario, why it is coming to the random nature of the channel. So that's why that is the key point of a fading channel, that due to the random nature of the channel, what will happen? The instantaneous signal power getting reduced smaller than the noise power. When it happens, for an example, suppose your transmitted signal is X, and your receive signal, due to the channel receive signal, you receive minus X. So X minus X is how much? 0. You have transmitted X, but due to the multipath, two multipaths, one has 0 phase, another one is 180-degree phase. So you will get X minus X, it is equal to 0. That is a deep fade scenario. If with the receive signal of 0, can you get the transmit signal? You cannot get. So that's happening due to this wireless channel. So what is the probability of defect? If you see, that is approximately 1 by SNR. That means what is the bit error rate of means your Rayleigh fading, the BR is how much? 1 by 2 SNR. Approximately it is 1 by SNR. That is actually same as your probability of defect. Okay, so that means if you want to reduce bit error rate, you have to reduce the defect. You see, think like that. See, if you want to reduce the bit error rate, we have to reduce the defect. That gives a key direction of doing research towards the wireless system, that gives evolution from the 3G to 4G. But how we are getting added this, how we are getting removed, we are getting a better wireless system which mitigate or which reduce the probability of defect. We cannot mitigate, but we can reduce it. How we are doing that is the diversity. The concept of diversity will come into the picture. There is various type of diversity, basically 3 type of diversity. One is time diversity. That means you transmit same signal at different time. Then you will receive. Diversity means what? Actually, you will transmit the same information through multiple signal paths. You transmit same information, but through multiple signal paths. What will happen that one path out of, suppose you transmit one symbol through 3 different paths. Each path has some defect, some probability of defect. So there is a highly chance that out of 3, one path can have less defect. Okay, probability of defect is smaller. So what will happen? Through that path, you can decode your transmit signal correctly. So that was not possible if you are not using diversity. Okay, this is a very simple fundamental way you can understand the concept of diversity. Another kind of diversity is frequency diversity. Same thing, it transmits signal, but a different frequency. Same signal you transmit, but in different frequency. You can use OFDM for this. Another one kind of diversity known as antenna diversity or space diversity, where we are going to discuss it. Well, 3 kind of diversity. One is receiver diversity, transmitter diversity, and MIMO system. Receiver diversity means what? There is multiple antennas at the receiver and single antenna at the transmitter. That is known as CMO system. And transmit diversity means what? Multiple antennas at the transmitter and single antenna at the receiver. That is MISO system. And MIMO, multiple antennas both side. Okay, let us come to the receiver diversity. Receiver diversity, first let us discuss single input, multiple output. Here you consider NR number of receiving antennas. Okay, for this NR number of receiving antennas and only one transmitting antenna. So what is, whenever we are going to design, we are considering any system, first point is we should write what? We should write the system model. System model means what? What is the relationship between transmitted signal and received signal, including the channel. So since you are using NR number of receiving antennas you are getting used, so your channel vector will be NR cross 1. So your receive signal will be a vector. Why? Because receive signal you are receiving through multiple NR number of receiving antenna. So that you can take as a vector form. You are transmitting one transmitting antenna, so your transmitting signal is only X. This is scalar. So Y equal to H vector into X plus NOS. Okay, this is the system model for receive signal expression, mathematical expression of the receive signal for CMOS system. Now the question will come, how we can decode the transmit signal. That technique will give you a better probability of error. Are you getting my point? So that means here, so whenever you are developing a wireless system, along with that you have to develop a decoder technique. So how to decode the transmit signal? So if you will not use the perfect decoder, so wireless system, even if you are developed, so that will happen, that will not give you a perfect less bit error rate. So to get reduced BER, what you have to do is you can use some technology that will be suitable for this CMOS system. Okay, that is known as maximum ratio combiner, or you can tell simply MRC. Using MRC, we can get better reliability for this receiver diversity signal. What is MRC? MRC is nothing but if receive signal will be what the receive signal after getting Y vector, you have to process the something in with Y. What you have to do? You have to multiply combiner vector. You have to combine. Basically, you have to combine the receive signal, but you don't combine like Y1 plus Y2 like this. You combine a weighted combining. This is a weighted combiner, you can tell. How to design, how to get these weights? which maximizes the SNR. That's why this expression we will get 1 by H norm into H vector. It's our mission. That means what will happen? Each of these channel coefficients you have to divide by H norm. Its norm will be there. That means you have suppose you have two channels. You have a two receiving antenna H1, H2. So two coefficients are H1 divided by H norm complex conjugate into Y1 plus H2 divided by H norm complex conjugate into Y2. That is the receive signal after applying this maximum ratio combiner. So whatever receive signal you get, then you decode by using simply any fundamental techniques like how you are decoding for AWGN channel. So before that, you have to apply the MRC. MRC is a basic equalizer technique for CMOS system. If we use MRC, what is the probability of error? Let us focus on this expression. This expression is what? Probability of error is approximately 1 by SNR to the power NR. NR is what? NR is the number of receiving antenna. SNR is generally higher because signal to noise ratio, signal to noise ratio means EX by this SNR is the definition we have taken for AWGN channel. That means with respect to AWGN SNR, we are comparing. Okay, like what you have done in previous case, without using diversity, what you are getting? This is the SN. This is the probability of error. 1 by approximately 1 by SNR. This SNR definition is what? EX by N naught. Okay, this is the constant for everywhere we are taking same definition. Then only you will can compare one wireless system to another system. So SNR, so here with Rayleigh padding without using any diversity, you got 1 by 2 SNR, which is very, very poor performance you will get in comparison to AWGN channel. Let us come to diversity. If you use diversity, what is this one? This one is 1 by SNR to the power NR. This one is this one. Now you check, you compare. There is 1 by SNR and 1 by SNR to the power NR, which is smaller. This one is smaller because SNR is always greater than 1. So you will get a smaller value. Smaller value to the power NR. NR is larger than 1. So you will get what? Smaller probability of error if you use diversity. That is the key point. Also, if you check here, this is the received signal after MRC. This H norm X, this thing. Then what is the diverse? What is the D fade? The D fade will be H norm square. Probability of H norm square less than 1 by SNR. The probability of D fade is 1 by SNR to the power NR. That now the thing is you can understand. See, if you use diversity, your probability of D fade is also smaller. Okay, so that's why you are getting a better type bit error rate in comparison to CISO system, where is only fading. This is Rayleigh fading is also CISO system. That means single input, single output channel. Okay, this scenario, single input, single output transmitter. Okay, you have a only Y is equal to HX plus noise. This scenario. Now diversity. Okay, so here, okay, probability of deep fade you got very small. So that using MRC, you will get better this thing. Next, let us come to the transmit diversity. What will happen here? You will use more number of transmitting antennas than and only one receiving antenna. Here the system model is a little bit deviated. It is H transpose into X because you have transmitted signal will be more. That means you have one, suppose NT transmitting antenna, you will get X1 to NT that will get added into the receive signal. So then what? Then now you can think that you cannot straightforward apply any detector decoder to get the better diversity. What you have to do is here you can use some precoding technique. That's so that is known as maximum ratio transmitter, MRT. Here it is known as MRT. One technique is known as MRT. That means what you do, transmitter side, instead of transmitting X, what is X? X is nothing but V into a symbol. What is V? V is a vector, precoding vector. This is the vector. If we use that, then only you will get this SNR, this exact performance you will get same as your previous case, CMO case. You will get same probability of error 1 by SNR to the power NT. Here you will get. Now there is a question that whenever you are using the transmitter precoder, the precoder is depending on the channel. So that is very difficult in practice to get channel at the transmitter side. Channel you can estimate at the receiver side, whereas it is difficult to get that transmitter side. So you can see clearly the precoding vector of the transmitter which is depending on the channel. That's why there's another kind of technology came that is known as orthogonal space-time block coding. Where what happens, you can use without using the channel. Okay, without using the channel knowledge of the transmitter, you still can get better probability of error by using orthogonal space-time block coding, or you can tell Alamoti coding. This has been developed for the two transmitting antennas. So in Alamoti code, you can get better. That means you can, if you use, we are not discussing it here. If you use Alamoti, that means what you can see, but Alamoti code can be applicable for two transmitting antenna. You can go more than that. You have to modify a little bit. That is means you can have a different space-time coding techniques that you can get the probability of error smaller than the yeah. So you will get better probability of error if you are going, or it is very close to the MRT system without the information of the channel at the transmitter side, without getting any knowledge of channel at the transmitter side. It is very difficult in practice. That means that's why OSTBC came into the picture, orthogonal space-time block coding. So now you can understand CMOS system you are using MRC, MISO system either you can use MRT or you can go for the orthogonal space-time block coding. So whenever you are going one system to wireless system to another, so you have to also develop the detection decoding techniques. So OSTBC, what will happen is orthogonal space-time block coding, you have to modify the transmitted signal along with the receiver detection signal. Okay, so you can interested students or who are participants, they can study, or faculties, they can study this OSTBC for different from first paper. You can see by the Alamoti, he is giving the complete details of for two transmitting antenna. Then you can understand what is OSTBC. This is a basic paper you can find in the from our IEEE website. Okay, let us come to the next diversity, that is known as MIMO system. When you have multiple antennas at the transmitter and multiple antennas at the receiver. So here you can see the mathematical system model is changing. What you have, y is equal to hx. H is a matrix. Previous two cases you have vectors. So here is a matrix. So each element of the matrix, if you are considering a flat feeding system, note that we had all the analysis, whatever analysis I have done is for the flat feeding. Frequency selective you can do, but for easy to understand, make a differencing all the different diversity techniques. It is better to take flat feeding. Then you can easily understand the advanced like frequency selective fading scenarios. Why we are considering flat fading? Because OFDM, including OFDM, you will get flat fading frequency selective to flat. So if you include MISO with, if you have a MISO system with OFDM, that is equivalent to your system MISO for flat fading. Okay, but there is a little bit modifications. You will do MISO with OFDM, but it is the analysis almost same with the flat fading scenario. That's why we are doing all the analysis with flat fading. Here, all the channel coefficient, how can define Hij means that this is the channel coefficient from jth transmitting antenna. This coefficient, the second coefficient is for with respect to transmitting antenna. First one is with respect to receiving antenna. Jth transmitting antenna to the ith receiving antenna. It is denoted by Hij, like H11, HRT. So accordingly, you will denote that first one is the transmitting, receiving antenna. Second is the transmitting antenna. You have different channel coefficients. So that will be their coefficients in H matrix. So now your questions, now you have the questions, how can decode the transmitted data? So this is the data is transmitted signal. You have the transmitted signal from all transmitting antennas. Suppose you have two transmitting antennas and two receiving antennas. Suppose, for example, you have two transmitting at one time, you can transmit two different symbols to the two transmitting antenna. Now the question will come, how can you decode these two symbols? Because this antenna will not only receive the data from this antenna is also receiving the data from this antenna. So both the data, all the transmitting antenna data is receiving at all the receivers. That's huge interference. So how you can get that? So there is different detection techniques you have. One is maximum likelihood ML detection. Another one is maximum ratio combiner. Here, interesting thing that you cannot straightforward apply for MIMO system maximum ratio combiner. If you apply, you will get significant error. You cannot get better things. Then, but there is a technique, as I told you previously, OSTBC, orthogonal space-time block coding. This OSTBC can enable you to apply MRC for MIMO system. That's the beauty of OSTBC. If you don't, without OSTBC, you will apply MRC, you will get BR significantly higher, because that it will not mitigate the interferences that occur. That means the first symbol will getting interfered by the symbols from transmitting from second and third antennas. That means that the main thing is fast, the symbol transmitted from the first antenna get interfered from the single symbols transmitting from second, third antennas like that. So how you can mitigate that one? So that you cannot mitigate by simply MRC. You have to use OSTBC, then MRC enables, then MRC you can apply. If you use OSTBC at the transmitter. For detail, you have to see what is OSTBC, then you can understand this thing. Okay, another one is zero forcing equalizer. This is another detector technique, zero forcing. What is the meaning of zero forcing? It is making zero to the inter symbol interferences, or you can tell that interlayer. The interferences of present the transmitted symbol of antenna 1 with 2 getting zero, nullify. That's why its name is zero forcing. Is forcing to zero that ISI. Or you can tell ISI, or you can tell interlayer, symbols of interlayer, you can tell simply. So better you can tell ISI, that nullify the ISI by using this equalizer. That's why it is zero forcing. Another one is advanced version of the zero forcing, that is known as MMSC. There is a negative point of zero forcing, where you have to be ensured that that should be full rank matrix. That is something you have to find the inverse of a matrix, that you have to ensure that it should be full rank. But that is not being possible practically always. That's why we can go for a MMSC receiver. So that is the MMSC and zero forcing. That is the advantage. Like MMSC is equal to zero. That means if you high SNR, what will happen? MMSC is then zero forcing performance will be approximately same. At low SNR, MMSC and MRC performance will be approximately same. So that's why MMSC is always better equalizer than zero forcing and MMSC. Whereas, however, if you are using OSTBC, then don't go for JDIF and MMSC. Not required. MRC is enough, because JDIF and MMSC, these two needs a calculation of inverse. Okay, inverse calculation is there in JDIF and MMSC. There is no inverse calculation in MRC. That's why MRC will not give you a high complexity receiver, but JDF and MMSC can give you due to the inverse computation complexity. That's why OSTBC will include with MIMO, with MRC, you will get a better receiver with less complexity. Okay, these are some key points of a MIMO system. Let us come to the next, what is multi-user MIMO. Multi-user MIMO means what? If you are going to communicate one transmitting antenna, base station has multiple antennas, and users, you can have either single antenna or more antennas. So that is scenario of multi-user MIMO. Whenever you're going to multi-user MIMO, previously all discussions we have done for a point-to-point system. That means one transmitter, one receiver. Multi-user means what? You have one base station, multiple users. So you will get additional challenges like multi-user interference. That means user one will get interfered from the received signal of user two, like that. So then you will get again challenge that how you can channel state information or channel in estimation can be done. Another one is user scheduling. Which user has to be communicated first, which is second, and what frequencies has to be done, allocations, that is known as user scheduling. So these are some challenges will come in multi-user scenario. Let us come to another technique that is known as multi-user massive MIMO. What is multi-user massive MIMO? Here, let me tell you, here the best station has 1,000 number of antennas, you can tell, more than 100. That is massive number of antennas, and user can have only one antenna. So what you can do is, this is the downlink and uplink communication. This scenario is known as multi-user massive MIMO. Okay. Here, why multi-user massive MIMO is better than only multi-user MIMO is that you will get high spectral efficiency and high energy efficiency. One very interesting point is signal processing technique is very simple. Why is that? You can use linear signal processing like MRC technique here, which is very difficult to applicable in only single multi-user MIMO system. That means without massive MIMO. If you're going to applicable MRC, if you're going to apply MRC, then you'll face problem. Okay, but you can use a simple linear signal processing like MRC over here, or uh, uh, that is, you can tell a simple signal processing because the linear multiplications will happen. So that's why you will get a better, by using simple signal processing techniques, you will get a better energy efficiency, better spectral efficiency, better reliability than multi-user MIMO. That's why there is a advanced version of that is very main important point is very important point of the massive MIMO to get better reliability along with the spectral efficiency. So here, this is the mathematical system model of the massive MIMO signal. If you have transmit signal X, so it is uplink system model. Uplink means you can see this one. So you can have uplink multiple users are transmitting the signal to the base station. What will happen at the base station? All the signals will get added, and you have this is the signals X consist all the signals from different users. Z is the channel matrix. M cross K. M is the number of antennas at the base station. Okay, K is the number of users. So due to that, you will have a M cross K channel. Okay, this is a huge channel. Many elements will be there. So this channel matrix. So this channel, that means this system model, you have to go do the processing. Let us see what is the channel capacity for the system model. So this channel matrix can be expressed like this. If H into D, that means here I have taken both the large scale and small scale fading. As you can know, the large scale means that is a path loss effect will happen. You know, the path loss, log, normal, shadowing, all these things. That will you can take as a square root of beta k. This is actually a large scale path loss model along with the small scale fading. So you have a channel matrix like that. So now what it can happen? Then you can replace this Z, whatever G you have taken here, by H into D. So you will get equation 6 will be get replaced by equation 8. Now let us see the analysis. What is the capacity? That let me tell you here. So in the uplink, if you can, okay, what is the capacity if you are going to apply linear detector? That is the my key point. So your receive signal is Y, right? Your receive signal is Y here. And what you will do? Apply some detector like A. This is the linear matrix A Hermitian into Y. That's it. So what you will get? You will get a receive signal at kth element of the receive vector. That means the receive signal that you are going to, that means base station has the receive signal of all the users. So for the kth user, so kth user receive signal. So this base station want to decode the kth user. Then only you can get the capacity related to the kth user, right? So then what is the signal? So you can let us take the kth user. So Rk that will get after this linear combining, or you can tell linear detector. This is the desired signal. That means the transmitted signal of kth user. What is this? These are interferences from the other users. Right? This is the other user signals that is get at the receiver. But receiver want to detect the kth user. Similarly, receiver has to detect other users, all user signals separately. Then he only can decode. He can send the data to different places. So that's the thing. So receiver signal at kth for kth to decode the kth user, what your RK is nothing but equal to this is the desired signal plus the interference plus noise. So what will happen due to this? What is the capacity? So you can apply the capacity expression. This is the capacity expression, equation 13. So this one numerator is the signal. That means you know that basic things. Log base to 1 plus SNR, right? From basic expression of the Shannon's capacity theorem. Based on that, you can have the channel capacity. Since there is no bandwidth multiplication, it is the best spectral efficiency, bits per second per hertz. And expectation we are computing means we are taking the random channel. That's why we are computing the ergodic capacity. That's the expectation. So leave it. The fundamental concept is here. You can see here. Here you have the signal power divided by the noise power from different. Sorry, this is the interference power of different users, and this is the noise power, only noise, AWG noise power. Now what you have to do, you can make it 0, then you have a better things. If you will getting higher, so this is getting smaller, so you will not get better capacity. Okay, you have to make nullify this thing or make reduce this thing. So how we can do that? So this simply, if you calculate like this, you will get what? See, here you have a non-zero. The denominator you can see it is completely non-zero. It is getting very higher with increasing number of users. If you are going more and more users, you are getting very high, very low SNR. This will be decreasing. So you will not get better capacity. Then wow, how this maximum will provide better capacity? Let us come to the, there is one technique, that is one important point, that is known as law of large number. Law of large number is taken from the mathematical, this probability theory concept. What is the law of large number? If we average the number of independent and identical distributed random variables, what you will get is, you will get that you will getting tends to its mean of a random variable. So due to that concept, P and P2 are same random variable will get its mean. The sigma square is the P square, expectation of the P square. So you'll get sigma square. If other random variable will come, they will get 0. That with this orthogonality property is approximate orthogonal property. Due to that only what you are getting, this part is going to be 0, this part. So then what will happen? You will get a very nice expression of the capacity log base to 1 plus something into EU. EU is the user energy or the power of the user EU. So this expression, the expression 14, you are getting, wow, if you are replacing the transmitted power by EU by M, then only you are getting. That's why this law of large number will come into the picture. What is M? M is the number of transmitting antennas at the base station. That means if M tends to infinite, what capacity you are getting? This capacity is very close to the AWGN capacity. That means the performance of the massive MIMO will be very close to the AWGN at a higher number of antennas. If you use higher number of antennas, that is the beauty of massive MIMO scenario. Then you have OFDM. OFDM is very, let us brief on OFDM. So as I told you, let us go to the ISI, that expression, what you wrote. So ISI, what you have, the inter-symbol interference you are getting. So inter-symbol interference, you are nullifying by using OFDM. What you will do at the transmitter side of the OFDM, you have a modulation, means you have serial to parallel converter, then you have IFFT, then parallel to serial converter, then you have to add CP, cyclic repeats, then transmit it, then remove cyclic repeats, they were serial to parallel, then you have FFT and all these things. What will happen? This addition of the cyclic repeats and removal of the cyclic repeats. If you remove it, something will happen here. If you remove, that means after removal of the cyclic prefix, the received signal will be simply a circulant matrix into X. Circulant matrix of the channel, which will look like this. G0 to GL minus 1. This is the L number of channel tabs. Then you have, this is the channel matrix. M is the number of subcarrier. That's the M cross M channel matrix. This circulant matrix you can get only if you use CP and remove the CP. Okay. So then you will get the circulant matrix. Then this circulant matrix, the beauty of circulant matrix is SBD. The circulant matrix SBD is F Hermitian gamma, the sigma into F. What is this F Hermitian? Is IFFT matrix. This FFT matrix. This side is IFFT. This is FFT matrix. And this is a diagonal matrix which contains all the subcarriers. That means frequency responses. If you can go mathematical wise, so finally what will obtain this expression? Received signal at frequency domain will be equal to transmitted signal at frequency domain multiplied with the channel frequency response at kth tone, or if k means kth subcarrier or kth frequency point, plus received signal. This you are getting how? By using transmitter side IFFT, receiver side FFT, and CP are the transmitter side, and you are transmitting including CP, the cyclic repeats you are including when you are converting the time domain. Then what you are doing? Yeah, here you are adding the CP. Then you are removing it and you are decoding. Sorry, you are applying FFT. Then you are getting what? This expression. This is the received signal. This is that means that now you can observe this expression with this expression. Here, you have getting higher ISI. There is no ISI there. That is the beauty of OFDM. Very simple. Received signal is simply a transmitted signal. Something is there, the channel plus noise. That's it. So that's why you can get the advantage of OFDM, that you are getting nullifying the inter-symbol interference by using the OFDM. And you can easily decode the transmitted signal. Transmitted signal will be nothing but equal to received signal divided by the noise, sorry, channel. Then we get transmit signal. Now you can see. So how till now what we have discussed is how you can nullify the ISI. You have the ISI, you are going to the OFDM. Then another direction is the antenna direction. You are going to the, you are nullifying, you want to improve the probability of deep fade, you are going to antenna diversity. So you can club it. You have a MIMO OFDM, one technology. You have a CMO OFDM, one technology. That means if you want to achieve frequency selective and along with the diversity, club OFDM with the antenna diversity. So that is the evolution that will happening in the 3G, 4G, 5G, all these scenarios. Like you have to see how this is getting improving what? Improving your probability of error. So if you are dealing with frequency selective, you will get ISI. However, if you are using OFDM, it is not only give you the better reliability, but also your receiver detection is getting very simple. You have a single tap transmitter multiplied with the channel. You have a single tap user, which is very difficult. With single tap user you are getting, which is a very easy thing of OFDM. That's why people are not leaving OFDM. for 5G, 6G, everywhere OFDM is the key physical layer technology. It's going 5G, it is also carrying to the 6G only. Okay, this is the beauty of this thing. Due to the CP, especially the CPU OFDM, there are also various variations of the OFDM. Okay, other variations like ZP OFDM is also there, zero pad OFDM. But that does not have this much of beauty. Why? Because you cannot have this kind of scenario as the receiver. Okay, this is the advantage of the cyclic prefix OFDM. Okay, let us come to the next. If you are going to the highly time varying channel, OFDM will not work. Why? Because it introduces intercarrier interference, which arises due to Doppler. That's why you can go for OTFS. OTFS, I'm not discussing much that. So OTFS only I will discuss one thing, this diagram. What will happen in the OTFS, instead of transmitting the symbols in time frequency domain, you can transmit delayed upload domain. So reason is what? Reason is, let me tell you one thing. This is the reason. Reason is what? If you are going to this one, if you have a channel, if you can see the channel in time frequency domain, see the channel in delayed upload domain. Time frequency domain, you have many taps. In delayed upload domain, you have only few number of channel taps. So if you are going to estimate channel in the time frequency domain, you have to estimate many taps. But however, you can estimate only few taps in the delayed upload domain channel. And another beauty is that if you are going this same channel, it has been taken after few milliseconds. Observe here. That's all tabs almost changing. Right? All tabs, you see the magnitude. Everywhere maximum it is changing. All the tabs heights. However, you see here, only this one, this grid point has shifted to here. Otherwise, remaining 3 is constant. That means you can take the channel in delayed upload domain is almost constant for a duration greater than the coherence bandwidth. This pictures has been taken where delta is a time which is greater than the coherence time. That's it. So during that time, even if the channel is, you have taken that greater than the coherence time, still you are getting constant channel in delayed upload domain. However, it is varying significantly for time frequency domain. That is the beauty of the channel. You can take analysis for the delayed upload domain. If you analyze the delayed upload domain, then you can get a wireless system, make a wireless system approximately slow fading. Okay, then the if you're analyzing time frequency domain. Now the question will come, you cannot apply, you cannot use delayed upload domain straightforward using the OFDM, because the mathematical equations you cannot get very easily. You cannot get a tractable, means you cannot track the channel, you cannot do estimation channel, you cannot do equalize the data. For that you need a very clear mathematical linear system model, then only you can do it. Okay, so to do that, that's why OTFS came into the picture. Due to this, all these stuffs are the receiver and transmitter. There are a lot of things. ISFFT, inverse simplicity finite Fourier transform, Heisenberg transform, you can, or you can tell this as the IFFT. Here you have Wigner transform and SFFT at the receiver side. So all this combining everything will give a nice expression like this. I can give you directly to that expression what you can get here. Okay, here's something where I written or not. Yeah. So here, receive signal in the time frequency domain. You can write in the delayed upload domain. This expression. Yeah, this expression. Receive signal vector in delayed upload domain is channel matrix. So this channel matrix is circulant matrix into X plus the noise. So this expression, the circulant matrix, block circulant matrix, can give you another method how you can decode the channel. That thing you will not get for OFDM. OFDM for highly time varying channel, so you will not get like this expression. You will get some IECI or intercarrier interference where you're getting problem. So that's why you have to study in more detail. You have to go for the OTFS papers, then only you can get these things. So there are few research works that in our group is doing is we have developed a lot of things like in MIMO OTFS scenario, beta rate for OTFS. So also RIS OTFS are working, and also we have recently one paper we have published in hardware architecture of OTFS transmitter receiver. Okay, so all the RIS, many papers we have, so you can see these papers. Okay, so thank you for this session. So if you have any questions, so let us discuss on that.
Thank you very much, sir. And in the chat box, there is one. Can we use relay channel in OFDM and OTFS?
OTFS. Yeah, you can use this is relay channel
Yes, sir.
only that you can use. Relay channel means what? Relay channel means it is a Gaussian random variable. The magnitude it follows the Rayleigh distribution. So channel is Gaussian. Channel random variable is Gaussian. Since the magnitude is following Rayleigh distribution, that's why you're telling it's a Rayleigh fading channel. That's it. Any questions, Sal?
And there is one more question. And what about high Doppler scenario? Can we use QAM in OTFS?
What are the high Doppler scenario? Can we use?
Can we use
Um,
QAM in OTFS?
QAM, that means quadrature amplitude modulation. We can use in
Amplitude
OTFS.
modulation, yes.
Yeah, yeah. QAM, there is nothing of QAM, QPSK with OTFS or OFDM. That is a separate thing. That is a constellation diagram. So you take the symbols and put it here. Like here, I told you the transmit symbols in what? Transmit the symbols in relay Doppler domain. These are actually these symbols are nothing but this X, K, L. These symbols are the QAM symbols. Whatever order you want, you can take accordingly. Okay. You can take QAM for both things. Any other questions?
There is no more questions. One more question, sir, from Ravi Kumar. What are the channel models that are more relevant in high mobility environments?
Okay, okay. So you have to follow Jake's model. So channel model, what you can do is 3GPP channel models are there uh, that you can use, but high mobility means you check about the Doppler, how much Doppler you are getting. So generally what I have seen that you can generate a mathematical channel model. 3GPP, from 3GPP you can take the delay parameters, and for Doppler what you can do is use the JEX model. JEX model means that you are using the velocity, different paths of the different velocities, and you can generate that Doppler shift by varying the angular cos theta I, the angle of arrival. You modify it, so you will get different Dopplers for different paths. Okay, that Dopplers, how much Doppler, that depends on what kind of velocity, relative velocity. So if you have relative velocity, so relative velocity, how much relative velocity, based on that you get a maximum Doppler, right? Then what you do, you have some maximum Doppler, so within that you can vary the Doppler shifts. Okay, then you can use that maximum Doppler nu max into cos theta. That is a model that I told you, use the JEX model. To get the delay, you take from the 3GPP parameters. They have the nice delay expressions. Take from there, and from delay for each tab delay, and for each path you will get delay information. You take from the 3GPP, and Doppler information you generate like the JEX model. Okay.
Thanks, sir. One more question from Sudhamani. What are various path loss models used to estimate the multipath in 6G?
Various pathless models.
Path
Okay.
loss models.
Yeah, the large scale pathless models you have to see like log normal. So you have to that depends on 6G. You are going to terahertz or millimeter wave. There are different pathless. So there are many pathless. Like so, based on main thing is what log normal you have studied already. So that is a pathless parameter. Lot of mathematical equations are there. You have to see some research papers on Terra. If you are 6G means I'm not getting 6G means there is many things. If you are particular about terahertz or millimeter wave or RIS based 6G, RIS based, so then your pathless will vary. So you have different expressions you have to take. If you are going to terahertz, then again you have to calculate not only simply pathless. The pathless include various parameters like antenna spacing. Like so if you are going to uniform linear array, the antenna spacing is there, so they will include in the pathless. So I cannot simply tell the what pathless model. Basically, you can follow the log normal basic model, but you have to include lot of additional parameters. Like there only you are including some pathless exponent. Like what you have to do here, you can include lot of like additional things like the distance between the channel, sorry, antenna, and then frequency, what frequency you are doing. And there is also something that is known as RIS, some parameter is also there, some coupling parameter and like that. They're also including in the this thing. So it depends. Yeah, 6G means use scenario. You can use terahertz, millimeter wave, or with RIS. So based on the application, you have to go for the pathless. Anything, any questions?
And one question from Ravi Kumar. Name some models for UAV-based communication.
UAV based communication, I don't know actually that thing. I have not done in UAV based communication. So that you have to search thing. I have not done any expertise on UAV.
UAV-based communication will be something like your high mobility environment, where the mobility is going to be in the order of the thousands of miles per hour. And so again, the 3D models that you are going to use it for your RIS, but confined to the mobility environment, which is going to be in the order of the higher mobility environment if it is going to work. So those models can be used for your UAV-based communication.
Okay.
Thank you, sir. And there
Is
is
there
no
any
more questions, sir.
Mr. Febin, you had some question, right?
There is no response from the Fabin Raju.
Okay, okay, fine.
Okay.
Okay. Thank you, sir,
I
for the clear
thank,
and insightful
sir.
session, sir, and covering the.
Thank you, Himanshu Mishra, for sparing his time out of his busy schedule and came over here for giving the lecture. So thank you very much, Professor Himanshu.
Thank you.